This video is part of a series on the xv6 operating system kernel. In this video, I'm going to talk about the kernel startup procedures. I'll go over the code in the file entry.S and the file start.c. Entry.S is pretty short. It contains a few assembly code instructions. Start.c contains two functions, start and timer init. All of this code is executed in machine mode, and at the very end of it, we switch into supervisor mode and jump to the main function. I'll also talk about timer interrupts. We'll see how they're set up in the timer init function, and we'll look at the code for the interrupt handler, which is called timervec, and that comes from a file called kernel-13.s. And I won't talk about all the assembly code that's in kernel-13.s, but I'll talk about this part of it. Let's begin with start.c, and I want to focus on this definition. Stack 0 is a stack of bytes, and remember we're running on a multi-core system. In fact, the constant in CPU is set to 8, so we can handle up to 8 cores. Each core will need its own stack. We will allocate a 4K page for each stack, and that's what's going on here. So we're executing the number of cores and one page for each. This bit of C magic here basically says, be sure and align this array on a 16-byte boundary. Okay, it's just normally a byte array, so it might not be aligned if we don't put this in here. That's what we're doing. I'm going to come back and talk about timer scratch in a second, but let's first take a look at the entry.c file. Here is the entire file. It's not too long, and let's take a quick look at this. This section command indicates that all of this code will go into a so-called section. Sometimes I use the word segment. That is a text segment. That is, it's executable code, and we see some assembly instructions here. We are defining a label _entry, and we're saying to the assembler, be sure and make this a publicly known global symbol, okay, so that it can be seen outside of just the assembly. There's another label down here, which is local, so that's what we're doing with the .global command. Okay, so what do we do? Load address. Okay, we're putting into the stack pointer register the address. Well, the goal here is to initialize the stack pointer register. And so here is the computation that this code is doing. The address of stack 0, that is that array, and then we're taking our core number, it's called heart ID in the Risc-V world. We're multiplying it by 1K, and so that's what's happening here. We load the address of the array into SP. Here we load 4 kilobytes into register A0, load immediate, and here we are reading from the control and status register called mHeartID. That is the control register that contains the number of the core, 0 through 7, and then we add 1 to that, so now we have a number between 1 and 8, and then we multiply that by the 4K that we computed in A0, so we multiply by 4K, and then we add that A0 to the stack pointer, and that gives us the point at the very top of the page for the stack for this core. Okay, so now we've got SP set up, and we're jumping to start. Here we see a call. We do not expect start to return, but if for some reason there's a bug, and it should, then we would resume execution here. This is a jump instruction, and we just go into an infinite loop and essentially lock up the core. Okay, next let's look at start.c. And it is right here. We see the entire function right here, and it will take care of several of the registers. and set things up for executing in main. And it will end essentially with a jump to main. So this is executing in machine mode. These functions that start with R underscore read various registers, and the ones that start with W underscore will write to the register. So here you can see we're updating the status register. We read it into some variable. We zero out the 2 bits that tell the previous privilege code for machine mode. Okay, so, and then we set those 2 bits with an OR to say the previous mode was supervisor. Well, we weren't previously in any mode, we've just started, but that we'll see that that's what we need when we finally execute the system return instruction down here. Here we write to the MEPC register the address of the main function. So again, the mret instruction down here will return us to whatever was previously executing. Nothing was previously executing, but by setting the status and the EPC, we're faking it. So we're going to be, if you will, returning to the first instruction of the main function. The SATP register normally contains a pointer to the page table. We initialize it with 0. There is no paging going on in machine mode, but when we go into supervisor mode, the value of SATP will determine whether paging is happening or not. So we want to zero that out to make sure that there is no paging when main starts. Now we have these 2 delegation registers, one for exceptions and one for interrupts. And we're writing something into these registers. We're writing all ones. And basically that means that all interrupts and exceptions are delegated to supervisor mode. So when an exception or when an interrupt occurs, it will not be handled in machine mode. Instead, it will cause an interrupt to the supervisor mode code, and it will get handled there. Timer interrupts cannot be delegated, so they're handled differently, but all other interrupts, and we really expect them only from the disk and the serial I/O device, and so that's what's going on there. Finally, this is the value for the interrupts enabled. I'm sorry, the register called SIE, which is whether interrupts are enabled. And we are reading the current value and then setting some bits and then writing it back. And what we're setting them for devices are allowed to interrupt. The timer is allowed to interrupt, and I'm sorry, although it doesn't happen. And this is for the software interrupt, the so-called software interrupt. These are all enabled. And so in particular, we're allowing the delegation to go into supervisor mode, and we're telling the supervisor interrupts enabled register that we want to enable these sorts of interrupts. Next, we have this physical memory protection, and we don't really use the physical memory protection system. Basically, we want to give the supervisor mode access to all of physical memory, so we write in these constants here to do that. I'm not really going to go into that, but basically this more or less disables the system. And then we call this timer init function to enable to set up things for the clock interrupts. And then we read the mHeart ID register, and that is the core number, and we save it in the TP register. So we write it to the TP register, and that it will allow our myCPU function to work later on to determine what CPU any code is running on. And then finally, we have some assembly code. We have the mret instruction. So we've already said we want to return to supervisor mode, we want to return to this PC, and so this mret instruction here will resume executing at the main function, the first instruction of the main function, and it will be in supervisor mode. So that's how we get into main. But before we do that, let's look at this timer init function. And I have that right here. So let's take a look at that. That is from start.c. And it's also fairly short. Here it is in its entirety. But let's go through this. So before I do that, I want to talk about the variable that is in start.c that we didn't look at, called timer scratch. So let me just point this out here. Timer scratch is, well, it's a two-dimensional array. We've got, well, in our case, we've got 8 CPUs, 8 cores, and each one of those has 5 64-bit words. So this is going to create an array of 5 words for each core. So here I'm showing this timer scratch array with all of its 8 elements, 1 for each core, and each element is going to look like this. Okay, it's going to have 5 double words. I'm showing the actual offset here. This is index 0, index 1, index 2, 3, and 4, but these are the byte offsets into this element of the array, if you will. And so we need that. So the first thing we do in timer init is figure out what core we're running on. So that just reads the core number. And we're going to be using that core number here. Remember that this core local interrupter has a couple of registers on it, and the time compare register is one of them. So there is one register per core. So this macro function here will give us the address of the register for this particular core. And what we're going to store into it is the current time. Okay, remember this is a preprocessor expression that gives us the address of the mTime register. So we get the current time. Okay, we're indirect here. We're getting the current time from this address, and we're adding the interval. Our timer interrupts will occur every, well, what is this, 1 million cycles. Okay, every million cycles we're going to have a timer interrupt. And so this is setting that register to this time plus a million. This is the current time plus a million. Okay, now prepare for we need to set up some of the, when the timer interrupt occurs, we're going to be using this piece of memory during the interrupt handler. And we need to store 2 things at this point. The address of the mTime compare register for our core, and we store the interval. The interval is a constant, and I'm not 100% sure why we really need to store that constant there, but perhaps in some future version we could have different cores running at different intervals. But that's the thing we're storing there. So what we're doing here is we're getting a pointer to what? Well, the timer scratch array. That's this array here. Okay, the element for this particular core, and we get the address for the 0 byte, the first part of that. So we're getting an address, a pointer to the address for these 5 words for the core that we're running on. Okay, and then we're setting that to be, we're storing that address in Scratch, and then we're setting the 3rd and 4th, or index 3 and 4 elements. Okay, 0, 1, 2. We're setting 3 and 4. We're setting 3 to the address of our mTime compare register. So again, this preprocessor function here, this macro function, given a core number, computes the address of the register for this core. And we need to keep updating it. So when we initialize it here, that means we're going to get an interrupt in 1 million cycles. But after that, we're going to need to add a million to it for the next interrupt and store the updated value. So we're storing the address of the register here, so we don't have to recompute it, if you will, each time we get the interrupt. And we're saving the interval, which is 1 million cycles. Okay, and finally we're writing into the mscratch register. There is an mscratch register for each core. It's one of the control and status registers. And so this core, the core we're running on, will contain a pointer to the block for that core. So that's what I'm indicating here, that we're saving in this mscratch register. This mscratch register will only be accessed in the interrupt handler for the timer interrupts while we're executing in supervisor mode. In other words, throughout the entire rest of the kernel, this register will be inaccessible. Only when we're running in machine mode will this register be accessible, and the only time we're in machine mode is during this startup and the execution of the timer init function, and then we will be in machine mode when the actual timer interrupt occurs. So that's why what we're storing in mscratch. mtvec, this is another register, and we're writing into this register the trap vector address. That is the address of the code that should be executed when a trap occurs. When that trap is handled by machine mode code, the core will handle it by jumping to whatever address we give it. So here we're storing in the mtvec register the address of the timervec function, which I'm going to show you that code in just 1 second here. And so now when we get the interrupt, we will jump to timervec. Then what do? We read the status register. This is the machine mode status register, and we update it and write it back. And what do? We set the interrupts enabled bit. So now machine mode interrupts can occur. So now at this point the timer interrupts can occur. And we also have a more control over individual timer interrupts. So we are reading the MIE register, that's for interrupt enable. This is an entire register, and the bits in it tell us more specifically what interrupts are enabled. And so we set the one for the timer interrupts to enabled. And then we're done initializing. And of course we were in the start function, so after we do the timer init call, we write our TP, and then we jump to the main function in supervisor mode. Now, so then the kernel executes along in supervisor mode, and everything's fine until the timer interrupt occurs. And the timer interrupt will throw us into machine mode, and will be handled by the machine mode code that's located at timervec. And so we're going to look at that next. What that's going to do is hand off the interrupt to a supervisor mode interrupt controller. So it's basically this code is going to be executed when the timer interrupt occurs, and what it's going to do is it's going to cause a software interrupt at the supervisor level. So that's what's going on down here. So let's take a look at this. This timervec is the starting address of the first instruction, and all instructions need to be 4-byte aligned in the Risc-V. We're not talking about compressed instructions here. That's for another video, another time. The timervec symbol needs to be exported so it's visible outside of this particular file, and so that the linker can find it, and so that when we are actually compiling and linking the code, where is it here? The use of this timervec symbol in the timer init function, the linker will plug in the right address. Okay, so that's why we export and make this a global symbol. Okay, so what do we do here? Well, now let's come back to this. Keep in mind we've just had an interrupt who knows what was going on. We could have been in user mode, we could have executing user code, we could have been anywhere in the kernel doing anything. So the point is, the registers that are in use must not be disturbed. This function will use registers 1, 2, and 3, and 0, I guess. And those are the only registers that will be updated, and they will be restored. So here what we're doing is we're saving the registers. At the time of the interrupt, aim_scratch points here. So the first thing we do is this read-write, which is a swap. Okay, so what it's going to do is it's going to exchange the value of A0 and aim_scratch. In other words, A0 will be written to aim_scratch, and aim_scratch will be read into A0. Okay, and then down here, we're going to undo that. So for the duration of this function, A0 will point to this. But then at the end, we'll restore A0. For the duration of this program, we are saving A0 in the aim_scratch register, and we're using A0 during this function to point to this 5-word area. The next thing we do is we save A1, 2, and 3 because we're going to be using them here. So we save them in offset 0, 8, and 16. So here we have a store double word of A1 into offset 0 from A0. A0 points at this point, it points to the beginning of this. 0 bytes offset, we store A1. Then we store A2 and A3. So we store our registers here, and then right before we return, we restore those registers from the same location. So this is a load double word. So we're loading from this location into A3, and from this location into A2, and from this location into A1, and then we're ready to execute the imret, which will go back to executing. When the interrupt occurs, our program counter will be saved automatically in the MEPC register, and the previous status and interrupt status will be saved in the status register, and then as a result of the imret, PC will be reloaded with whatever was saved. So we see some stuff going on with the trap and the imret that's not really visible here, but that will be happening. Now, here's the meat of it here. Schedule the next timer interrupt, and by adding this interval, that's 1 million, to the hardware register called mTimeCompare. So fortunately, we've saved the address of our mTimeCompare register, that is the register for this core, at location 24, and the interval at 32. So that's what we're doing here. We're loading from this place into register A1. So now A1 points to the hardware register. We load the value, which is 1 million, into A2. And then what we're doing is we are loading the current time, the current value of mTimeCompare, right? That's in A1, okay, with 0 offset. We're loading that into A3, and then we're adding A2. A2 contains 1 million. So this is where we add 1 million to the previous value of the mTimeCompare register. And finally, we need to store it back. So here we loaded it, we added to it, and then we stored it back. Okay? So now that will essentially schedule another interrupt to occur in 1 million cycles. 1 million cycles minus however many cycles have been executed to this point, of course. To this point where we load. Actually, sorry, I misspoke. We're just adding 1 million to the time compare. So it's not less anything. It's just adding 1 million to it. So we get a timer interrupt every 1 million cycles. And finally, we have to raise a supervisor software interrupt. This will interrupt the kernel. It will only interrupt the kernel if the kernel is ready. So it depends on whether interrupts are enabled in supervisor mode. But in any case, we raise the interrupt to be handled either, whenever we go back to the supervisor mode, or whenever the supervisor mode code allows it. But we do that by loading this value into A1 and then writing it into the interrupts pending register for supervisor mode. So here is the particular bit position that corresponds to supervisor software interrupts, and we're storing that with a write to the control and status register called SIP, supervisor interrupt pending. That makes the interrupt pending. We're in machine mode, so it won't happen immediately. Then when we return to supervisor mode code, it depends on whether the interrupts are enabled in supervisor mode. If the interrupts are currently enabled in supervisor mode, then the interrupt would happen immediately. But if the kernel is doing something that can't be interrupted, and it has temporarily disabled interrupts, then that interrupt, the supervisor software interrupt, will remain pending. But at some future point, the kernel will enable interrupts, and this software interrupt will occur. The kernel will then have a trap in supervisor mode, and it will interpret the software interrupt as being a timer interrupt, because that's the only thing that could be causing it, and will basically switch out the current user mode thread. It will do a context switch. It will do the processing it would do at the end of a time slice, which we'll talk about in some future video. Okay, thanks for watching, and I'll see you in the next video.